Currently, NASA Ames is involved in the High Angle of Attack research program. Smoke is released from a research vehicle at a high angle of attack. The smoke indicates the location of the vortex burst from the LEX or leading edge extension. Scientists are developing a CFD code to simulate the flow around the F-18 aircraft. Here we see the results of the computations solving the Navier-Stokes equations using overset grids. The development of the four-body and LEX vortices and the burst of the LEX vortex can be seen. In this image, we can clearly see the separation lines on the four-body, LEX, wing, and leading edge flaps. Helicity contours help to visualize the off-surface flow field structure. The comparison between flight and CFD data show a very good agreement. The object of this intercenter program is to provide more understanding of the high angle of attack regime through flight testing, wind tunnel experiments, and CFD simulations. Powered lift aircraft, such as the Harrier, use high-temperature jets vectored towards the ground to supply a significant fraction of the required lift. This infrared visualization of the Harrier indicates the concentration of heat in the jet plume region. This plume may cause damage to the landing surface and aircraft. Isolating the jet exit and ground region, this simulation shows the hot jet impacting the ground plane. Temperature contours are plotted in the fluid and solid. As the jet impacts, heat is conducted into the concrete, forming a concentrated hotspot. the surface temperature rapidly approaches the jet exit temperature. An identical computation was performed with a steel surface and is compared to the concrete temperature contours. The flow fields are identical until the jet impacts. Less thermal energy is imparted to the steel plate than to the concrete. The shape and propagation speed of the vortex structures in the shear and impingement regions depend directly on the interaction with the surface material. Penn State Artificial Heart is being developed through an interdisciplinary effort of medicine and engineering. In previous years of NASA's involvement, the flow through the chamber and valves were studied separately. This year, the flow through the entire configuration is simulated. Shown here are particle paths released from the inflow valve at the beginning of each cycle. The particles are colored by release height. The vortex created in the central portion of the pump provides good wall washing over the entire chamber, thereby reducing the chance of blood clot. Here we see vorticity contours on the surface of the artificial heart. The lowest vorticity value is blue, the highest magenta. High vorticity magnitudes indicate high shear regions. Large shear stress in the flowing blood and near solid boundaries may damage the blood cells.
In the margin of an ancient book, the 17th century mathematician Fermat stated that the equation x to the m plus y to the n equals z to the n cannot be solved with non-zero integers x, y, z for any integer power n greater than 2, and then wrote, "I have discovered a truly marvelous proof that this margin is too small to contain." The statement remains unproven to this day. Computer graphics can help us visualize the nature of mathematical ideas like Fermat's theorem. Fermat's equation itself is just a cone for n equals 2, and there are many integers, such as x equals 3, y equals 4, and z equals 5, that satisfy the n equal 2 equation. If we vary n continuously, the cone changes to an inverted pyramid. The slices at constant z are two-dimensional superquadrics with exponent n. Varying n smoothly interpolates between circles and squares. The curve passes through many integers as n varies, but somehow just misses hitting any integers for integer values of n, unless n equals 2, the perfect circle. Just as one can ray trace a deformed solid by following a deformed ray through the undeformed shape, we can deform the integer grid instead of the Fermat curve. Recent attempts to understand Fermat's last theorem have explored the relationships between number theory and the algebraic geometry of surfaces. Instead of looking for intersections of a cone with a 3D grid of integers, we look for intersections of a real 2D curve with points whose coordinates are ratios of integers. In this framework, Fermat's equation extends to a two-dimensional surface embedded in the four-dimensional space called CP2, the complex projective space of two complex or four real dimensions. For each n, the surface becomes a patchwork quilt of n-squared pieces that surround the origin and extend to infinity in two complex dimensions. To visualize what is happening inside the surface, we can sweep the surface out from the outside in, or cut into the inside, or use transparent displays. For each integer power n of Fermat's equation, the surfaces have the topology of spheres with more and more teapot-like handles. To see these as the closed surfaces they really are, we transform the surface so it lies within a compact sphere. The clearer our mental picture of the problem becomes, the more likely it is that we will gain intuitive insights that will finally allow us to solve the problem. In fact, wait, I think I see a way to prove the theorem. Yes, I can prove it, but the proof is a bit long. Now, if only I could explain it to you before I run out of videotape.
We're watching the evolution of a cosmic jet as modeled by a group of scientists using the Cray YMP 8864 at the San Diego Supercomputer Center. In all of these images, the jet is a thin streamer in the middle of the picture. All around it is the backflow or cocoon from the jet's leading edge shockwave. Cosmic jets, first observed in the 1950s, appear to be long streamers of hot gases. The gases are expelled from the active centers of galaxies and can extend out as far as hundreds of thousands of light years. Scientists believe that a jet may travel at nearly the speed of light and that its energy may come from a black hole. To date, some 200 cosmic jets have been identified. One outstanding question is, why do the jets tend to remain together, collimated over enormous distances? Why doesn't the backflow just dissipate into the surrounding intergalactic medium? Scientific team leader David Payne says that computer experiments are helping to achieve a better understanding of these mysterious objects. Billion years ago, a cloud of hot, swirling dust and hydrogen gas gives birth to our sun and planets. As the cloud spins and collapses inward, it flattens into a central mass and surrounding disk. Dust and gases in the disk form other smaller condensations, each spinning about its own center. Gravitational condensation heats the central mass. Density increases dramatically and fusion begins. Energy is released and our sun flares into existence. The solar wind of the newly ignited sun blows away leftover dust and gas in the vicinity of the inner condensations, leaving the rocky inner planets, Mercury, Venus, Earth, and Mars. In the outer reaches of the disk, the solar wind is weaker. The remaining dust and gas condense into the large gaseous planets, Jupiter, Saturn, Uranus, and Neptune. This scenario leaves us with many questions. How does this process begin in an initially homogeneous cloud of dust and gas? If it happened here, could it happen elsewhere? One job of the Hubble Space Telescope is to try to find evidence to answer these and other questions about our universe.
These animations were made on pneumatic videotape using a DiaQuest animation controller. The video was generated using a Paratech frame buffer or Stardent Titan or Silicon Graphics Iris workstations. The first animation describes the early evolution of a supernova remnant, the gas expelled from the exploding star, as well as the interstellar gas it piles up. The calculation follows the Eulerian dynamical flow of a radiative gas. The image shown represents gas density. Initial conditions were dictated by constraints observed from a young supernova remnant in the Large Magellanic Cloud, a companion galaxy of our own Milky Way galaxy. Note particularly the formation of instability-produced cloud fragments at the outer edge of the remnant. The simulation was performed by Jeffrey Knair and John Morse as part of an astronomy class taught by Alan Ciano and Wayne Christensen at the University of North Carolina, using the PSC's Cray YMP in the DrawCGM graphics package. This animation, by Mark Berger, illustrates fractal or Markov chain image encoding techniques. Each of the images in this transformation is defined by 4 3x2 matrices, containing a total of 24 floating point numbers. Certain images define points in a 24-dimensional space. Transformation between these images are generated by moving in straight lines through the 24-dimensional space from one known point to the next. The goal of this research on Markov chain image encoding is to discover the dependence of the images on their defining matrices, in the hopes of coming up with better ways to do the inverse problem of finding the matrices that define a known image. This animation, by David Deerfield, Darren York, and Gray Lorig, also shows the dynamics of a segment of DNA. The molecule has been simplified to better show the changing relative positions of the base pairs. The animation was rendered with the OASIS ray tracer. This animation, by Jim Ellis of the PSC, shows the time evolution of memory usage on a Cray YMP. Each point represents the total status of memory at a given moment. Its location is specified by interpreting the fraction of memory associated with jobs in each of 3 states as coordinates in space. Points appear at the time the data was taken and fade as time passes, so that the evolution of the memory usage statistics can be seen. This animation, by Rick Sideritz and Cy Evans of Shadyside Hospital in Pittsburgh and myself, shows a reconstruction of the lymph node of a cancer patient. The node was removed and sliced into sections, which were digitized. This provided data for a Marching Cubes algorithm, which produced P3D models for each of the colored surfaces shown. These models were merged and colored to produce the final lymph node model. Each color shows cancer believed to be descended from an individual metastatic hit in the node. Lymph flows through the node from right to left. As metastases of cancer enter the node and begin to grow, they are carried down the node by the flow. This causes the cancer to grow in striking tree structures within the node. This animation is our version of JPL's famous LA the movie. The model over which we are flying was constructed from terrain data for Los Angeles. It is composed of triangle strips containing a total of roughly 100,000 triangles. To produce the flyby, a user interface module was written, which actually simulates the dynamics of an airplane in flight. Its flight path was recorded as it was flown over the model, and the path data was used to make the animation. This user interface can now be used to produce a flyby of any P3D model. The jerkiness is caused by ringing and spline interpolation of the flight path data, but it reminded us so much of our last flight into Los Angeles that we decided to leave it in the animation. As we descend towards Catalina Island, the polygon resolution of the geometry becomes apparent. The flight dynamics at the user interface also become apparent as the plane stalls momentarily before climbing away from the model.
This is an interactive exploration of cold fronts moving across the North Atlantic using the Viz5D software written at the University of Wisconsin and running on the Stardent ST2000. The region of interest here is the North Atlantic and Europe, and North Africa and Eastern Canada, and we can see Greenland up there in the north. We have a three-dimensional box that we can rotate around, and we've turned on a constant moisture surface and low-level pressure isobars. We're going to make the surface a bit transparent to be able to see the isobars beneath it. Now we've hit the animate button to start the time dynamics. And we can see the cold front developing as that moisture peak across the Atlantic between the low pressure system up over Canada and the Azores High. There we see the front pivot, and a deep low pressure system will develop northwest of England, and England gets hit by the front, which had record winds, heavy storms. Then we see a second front developing now over eastern Canada. We're turning a jet stream on and off to see how the jet stream correlates with the front. And indeed, the jet stream and the moisture surface correlate with each other very clearly. The little clock hand up in the upper left-hand corner is hit 12, which means that we recycle a data set. We're cycling over and over again through a one-week data set at 1 hour time steps. There we can see the front defined by the jet stream and the moisture moving ahead of the front. Now we're going to stop the time dynamics, turn off the pressure isobars and make the moisture surface opaque. And we're going to rotate around and take a low-level view of this and zooming in over Europe and the Mediterranean. Now, as we start the time dynamics, you can see a wave moving in through this jet stream, and the wave is going to push that pivot around in the front. Now the front hits England, and then as the front moves across the Iberian Peninsula, the cold air will hit the warm water of the Mediterranean, and we'll see an explosion of moisture over the Mediterranean. Now we can see the second front moving in south of Greenland. Now as the clock hand hits 12, we'll recycle a data set. We'll turn off the moisture surface and turn on a light blue vorticity surface, which will show us the areas of rotating air and wind shear. We've also turned on trajectory lines, which show us the motion of individual air parcels. The wind speed surface, the vorticity surface, and the trajectory lines together give us a very detailed look at the airflow.
AZT, the azidothiamidine molecule, is shown here in a stick figure representation. Here it is superimposed on thymidine, a part of DNA produced after HIV infection. AZT is used in the treatment of persons with AIDS. Its effect is presumably due to its similarity to thymidine. This model emphasizes the bonds between the atoms in AZT. In another model, the atoms are shown as spheres. However, it is really the electrons that are doing the chemistry, and in order to study this effect, we performed Gaussian 86 calculations on AZT and rendered the electron density in the highest occupied molecular orbital. Here, the growing electron density represents lower and lower electron densities around the nuclei. The higher electron density contours become visible when we render the lower densities transparently. Here, thymadine's electron density is shown using the same colors and contour levels. In this volume visualization, we used a volume of 200 by 160 by 140 voxels and rendered the contours using small spheres. In order to understand the effect of AZT, we need to look carefully at not just the similarities, but the differences between AZT and thymidine. To do this, we have carefully aligned AZT with thymidine and subtracted corresponding elements of the two voxel matrices representing the electron density of AZT and thymidine. Contouring in the same way as before, we clearly see the lower electron densities of AZT shown in purple and blue, and the greater electron densities in shades of green. Using this difference technique, we can suggest new molecules. Computational chemistry provides not the answers, but a rational basis for drug design.
Grumman Data Systems has developed computer graphics techniques to model natural features using ellipsoids textured by a mathematical function which modulates shading intensity and translucence. Dynamic behavior of clouds, smoke, and fire is simulated by manipulating the ellipsoids and their texture patterns. This forest fire animation was produced by combining these graphics techniques with a heuristic dynamic model. A defined region of fire is expanded with time depending on the direction and speed of a specified wind vector. Within the expanding fire region, a simulated heat function is computed at regularly spaced intervals to drive the growth of fire and smoke ellipsoids.
Yellowstone National Park has been the topic of a controversy in fire control policies since the ravaging fires of 1988. Scientists are studying a critical issue. Should forest fires be suppressed as they occur, or should natural fires be allowed to burn? Here, a magnified map of Yellowstone is shown. The study area is highlighted in color. Non-destructive tree core samples provide data about the fire history of Yellowstone. To To understand the forest dynamics over time, areas of vegetation are color-coded according to age. The youngest forest areas are shown in yellow, the oldest in dark green. Red indicates fire, and black represents non-vegetation. This map shows what actually happened over the past 300 years. During the early years, there were small fires throughout the park. These promoted wide diversity in the age of the forest. Small fires turned the old dark green forest to young forest, represented as yellow. Animals utilized portions of the forest most appropriate to their needs. From 1872 to 1972, a policy was enacted to suppress all fires. Notice how the forest ages. The advanced age of the forest, combined with drought and high winds, created favorable conditions for the fires of 1988. The actual landscape dynamics, seen on the right, are now shown beside a fire-absent simulation. This simulation is what would have occurred had there been no fires for the past 300 years. Note the lack of landscape diversity as the forest grows older. The tall, old foliage prevents the penetration of sunlight that promotes the growth of forest floor vegetation. Theoretically, a forest in such a condition would be susceptible to a series of large fires. As to the question of whether the 1988 fires would have occurred without the fire control policy, this animation shows that similar large fires have occurred naturally in the past.
This visualization is based on quantum electronic structure theory. It was used to calculate how a chlorine atom and a chromium metal ion react to form chromium chloride. As the chlorine atom approaches from the right, electrons shift from the blue to the yellow regions. This same data is shown again using isosurfaces of electron density differences. Electrons are shifted from the blue region toward the growing magenta regions. The green surface shows the areas where no electron change occurs. This reorganization of electrons forms an energetically stable molecule, thus satisfying the laws of thermodynamics. This sequence is based on local density functional theory. It was used to determine the energies and shifts associated with lithium as a promoting agent. Shown here is a 48-atom magnesium oxide crystal with a red lithium atom substituted in a face position. The effect of lithium substitution is represented by electron density differences. Blue denotes electron loss, and yellow denotes electron gain. Another class of solid catalysts are called zeolites. Here, two sequences illustrate benzene transport through a zeolite. In each case, the graph on the left displays the energetic stability of the move. The electron density distribution is represented by the colors surrounding the atoms. The model system is a 72-atom ring molecular cluster. This cluster was taken from the crystal structure of a zeolite called phlogisite.
The Los Angeles, California basin is home to over 10 million people and one of the worst smog problems in the world. Situated on the Pacific Ocean, it is bounded to the north and south by mountains. Satellite imagery shows the various regions and the extent of urbanization in the basin. To understand how pollutants comprising smog are formed and transported within these regions, researchers have developed a complex mathematical model describing the evolution of smog. The domain of the model is shown here. Cars are one of the sources of reactive organic gases, carbon monoxide and nitrogen oxides. This simulation uses actual measurements to show the transport of these pollutants over a 3-day period. Each green particle represents 10 tons of reactive organic gases. Each yellow particle 10 tons of carbon monoxide, and each red particle 10 tons of nitrogen oxides. Winds from the ocean, shown as arrows, sweep these emissions inland. Weather conditions can cause the air to become trapped in the basin. Trapped organic gases and nitrogen oxides react in the presence of sunlight to form ozone. This air pollution model is used to display the resulting atmosphere. The invisible ozone is represented as a green cloud. Concentrations peak in the afternoon downwind of the heavily populated areas. Carbon monoxide, represented as a yellow cloud, peaks during rush hour in the downtown area. These graphs show the average and peak pollutant concentrations on the ground. A red line indicates the national air quality standard. Nitrate, sulfate, and carbon particles make up the visible components of smog which build up and obscure the sunlight. The Los Angeles smog cloud has become well known in the last 5 decades. In spite of stringent controls, the problem threatens to become worse. However, by using mathematical models and visualization, researchers and regulators can identify effective solutions that promise to improve the quality of air.
When you put on a head-mounted display, you enter into a computer-generated world. This is a protein molecule that I see in front of me, and as I look up and down or turn my head from side to side, I see the image of the protein molecule move around in my field of view as if it was there in a fixed position in space right in front of me. The position of the head is tracked by the little sensor that you can see on the clear plastic piece above the black viewer. And if I get closer to the molecule, it gets bigger. This is a manual input device that I use to manipulate things in the virtual world and initiate commands. The little white square I see right on top of my own hand, and when I move my hand around, the white square moves in a corresponding fashion, and I can also rotate it. There are two push buttons on the manual input device, and the hand shape changes to show what sort of commands have been initiated. So the arrow signifies flying through the virtual world, and as I turn my hand to point in different directions, I translate through the virtual world in the direction my hand is pointing. So here I'm flying around through the protein molecule. This is a different manual command that's shrinking the molecule down until it's about the size of my fist. And now I'm using another manual command to expand it again until it's big enough that I can fly through it. Here I've grabbed a second molecule, a drug molecule, and I'm moving it around trying to find a docking site that I can plug the drug molecule into in the receptor protein. This is a force feedback arm that we use in conjunction with the head-mounted display. It can apply forces and torques to the hand through the hand grip that I've got hold of there. And here I'm moving the yellow ball around by moving the hand grip. And if I move the yellow ball down until it hits one of the triad of lower balls, I feel a force through the hand grip when the collision takes place. The hand grip can move in all 3 degrees of translational freedom and 3 degrees of rotational freedom. And the 6 motors up in the large assembly mounted to the ceiling can apply linear forces and torques to the hand. And these forces and torques, of course, are dependent on what's happened in the virtual world that's being simulated.
Our first program is on similarity, all about things that have the same shape but are different sizes. With our trusty expando ray, we can change the size of any geometric object. It doesn't matter where we aim it. The center of scaling can be anywhere. The scaled triangle is still the same shape. And all the angles stay the same. This gives a nice proof that the angles of a triangle always add up to a straight line, 180 degrees. Just shrink the triangle down to nothing, and all you have left is the angles. Another thing about similar shapes, ratios of corresponding sides are the same, and internal ratios are the same. The Greek mathematician Thales used this to find the height of a column by comparing shadows. These two triangles are similar, so ratios of lengths are equal. Just pick a time when the shadow of Thales' staff is equal to its height, and the column shadow equals its height. You can also scale three-dimensional objects. But when you do, you multiply the volume by the scale factor 3 times, and areas by the scale factor twice. Now the weight goes as the cube of the size, and the cross-sectional area is the square, and that's how we can get rid of our giant bugs. We just point out to them that their legs are proportionately too thin to hold them up. The circumference of any circle is a little more than 3 times its diameter. In other words, the ratio of circumference to diameter is about 3.14, a fundamental constant of nature called pi. The area of a region inside a circle is some number times r squared. This factor a is another fundamental constant. Guess what? It's the same value, pi. Why is this? Let's unwrap half the circumference for reference. Then chop the discs into sections. I would say pie slices, but I'm too nice. Now rearrange them into a sort of parallelogram. Make the sections smaller and smaller with more and more of them. The parallelogram slowly becomes a rectangle. Height is r, width pi r, half the circumference. Area, pi r squared. And yes, I have heard the one about pi r round. Let's try it another way. Slice the disc into concentric rings and pull them out straight. Make the slices narrower and narrower, and you get a triangle. Altitude is r, the base equals the circumference, 2 pi r, so area, half the base times the altitude, is pi r squared. The digits of pi never repeat. One of the most practical applications of supercomputers to date has been to calculate the 1/1000th digit of pi, a truly transcendental experience. We won't go that far here. It's 9. Pi shows up wherever circles do, in the areas and volumes of surfaces of revolution. But it also shows up in places where circles are not so obvious. Suppose you decide to drop a needle on a floor with floorboards twice as wide as the needle length. It can land crossing a line or not. The probability that the needle crosses a line is 1 over pi. Here's a weird one. Put a yellow dot on each grid point where the x and y coordinates are relatively prime. Another way of saying this is, put a yellow dot at each grid point that's visible from the origin. The dark dots are hidden behind the bright ones. In the limit, the probability of seeing a grid point is 6 over pi squared. Pi has something to do with prime numbers. What's up next? Future programs will deal with things like the shapes of polynomials and trigonometric functions, locus problems, platonic solids, all to show that mathematics is the second most interesting thing you can do.
The skin is more than just an outer covering. It's an organ with multiple functions, of which protection against invasion by microorganisms is a most important one. But this is only effective as long as the skin is intact. Any injury to the skin creates a wound, and the body responds spontaneously. Let's take a look at what's going on inside a wound. Here, we'll meet several actors on the way to their specific roles immediately after injury. The intermeshing events activated by injury can be structured into 4 main phases. The first phase in wound healing is called the vascular response. When an injury happens, the arterioles dilate. Blood can easily stream into the wound, which is effective as a first rough cleaning process. The widening of arterioles also creates an increase of capillary permeability. This enables platelets, fluids, and erythrocytes to get into the wound area, where they are needed for further healing processes. When the actors are on stage, arterioles are contracted to control blood loss. The second phase is termed coagulation cascade. Destroyed and exposed collagen fibers release various substances in order to attract great amounts of thrombocytes. Caused by the same substances, the thrombocytes get sticky and adhere to the injured collagen tissue as well as to each other. During this aggregation phase, the thrombocytes send out signals in order to activate an enzyme called thrombin. Thrombin transforms fibrinogen into fibrin. Immediately, the formation of a fibrin mesh is initiated. It serves as a scaffolding upon which the erythrocytes and cellular debris can be captured. As soon as the fibrin mesh has been established, the inflammatory phase of healing begins. It's the most critical and important one. The wound is inevitably strewn with foreign bodies, bacteria, and cellular debris, which can cause inflammatory reactions. These materials secrete different substances, one of which attracts granulocytes. The granulocytes detect cellular debris, foreign bodies, and bacteria, and invalidate them by releasing specific enzymes. This is a cue for monocytes to appear, now being enabled to take in the invalidated material. By means of this process, the monocyte is dramatically transformed into a macrophage. Macrophages are able to catch and to devour great amounts of bacteria and cellular debris. They also release factors which cause fibroblasts to migrate into the wound, thereby initiating the connective tissue phase of healing. This phase is characterized by an intense activity of the fibroblasts. From the surrounding tissue, they swarm into the wound like squadrons. Reaching their destination, the fibroblasts start producing procollagen within their ribosomes. The procollagen molecular chains wind up to form triple helices. After being extruded, these triple helices are linked together and combined with proteoglycan, thus forming collagen fibers, the major component of strong scar tissue and the basic structure for complete and successful healing.
Invertebrate Models was designed as a tool for classroom instruction in invertebrate zoology. This subject requires students to learn the functional anatomy of over 30 major groups of animals with a far greater variety of structures than is presented in a course on human or vertebrate anatomy. Understanding of animal function is based on three-dimensional structural relationships, but these are often difficult for students to observe in a classroom or laboratory environment. Formaldehyde preservation usually distorts anatomy and changes color. Observation through a microscope prevents rotation and drastically limits depth of field. The use of software models can provide realistic representations that are superior to photographs in cinematic formats. Software models can also portray animals that are rare or difficult to obtain as living specimens. Solid models can also provide realistic representations of abstract concepts such as hypothetical ancestors and fossils that exist only as flattened remains. Models are constructed using Swivel 3D by assembling complex structures from simple components. Textbook illustrations and live specimens are used as blueprints to ensure anatomical accuracy. Invertebrate models also calls attention to the biodiversity crisis. Of 30 million living species, it is estimated that nearly half will become extinct in the next 100 years, and over 95% of these will be invertebrates.
These demos show a sampling of volume visualization and rendering techniques over a variety of scientific applications. The demos are running on Sun visualization workstations, ranging from a SparkStation 470 with Sun Vision to a SparkStation 370 powered by Sun's new visualization accelerators, the VX and the MVX. These accelerate Sun Vision's tools and libraries into image processing, volume rendering, photorealistic rendering, and 3D graphics. This is the bow shock of a stellar jet from a newly formed star. Blue represents a high-density contour showing the outline of the bow shock. Yellow and red are isosurfaces of sulfur and hydrogen emission intensities. The rendering, done by John Morse at the University of North Carolina, shows how the sulfur and hydrogen emissions are enveloped by the bow shock. Morse used several of Sun's visualization tools to study his data. He used the volume rendering tool in Sun Vision to create volume displays of the bow shock, the sulfur emissions, and the hydrogen emissions separately. He extracted the surfaces from these volumes and combined them using Sun Vision's geometry viewing tool. The Sun Vision high-quality rendering tool did the final rendering of the frames. Morse used Sun Vision both on a SparkStation desktop and on the accelerated SparkStation VX plus MVX. A new volume rendering technique called splatting is shown here as it is running on the SparkStation VX plus MVX. Splatting, developed by Lee Westover while at the University of North Carolina, uses a forward mapping technique. Here, the rendering of an RNA molecule is shown in the right window, and the finished result is shown in the left window. Westover used the C developers tools that come with the VX accelerator to port his algorithm to the SparkStation VX plus MVX. This is a movie loop of frames rendered with the splatting technique. This data is 96 CT scans of a head, each 256 by 256. The gradient strength at each voxel is used to isolate surfaces of skin and bone. By modifying the opacity of the skin, the underlying bone can be exposed. Each frame of the movie was rendered on a SparkStation 370 VX plus MVX in 5 to 85 seconds. The images of this movie loop were rendered with Sun's volume rendering tool, SunVoxel, which uses a ray casting technique. The renderings are of a supercomputer simulation of the interaction of current flowing in two colliding cosmic strings, which are theorized to have been created during the Big Bang. Sun's volume rendering tool lets the user assign unique colors and opacity values to ranges of voxel values within the volume. This data is courtesy of Richard Matzner from the Center for Relativity at the University of Texas. The images of this movie loop were also rendered with Sun's volume rendering tool. Here, 61 MRI scans, each 256 by 256, were rendered using the ray casting technique. Volumetric editing was used to remove the skin and bone substances on one side of the head in order to reveal the structure of the brain surface underneath. This data is courtesy of Jeff Shaw from Vanderbilt University. Here, 400 slices from a seismic scan of an oil field have been rendered with the Sun Voxel volume rendering tool. This movie loop is running with the Sun Vision movie tool on a Spark Station 470. The user defines substances in the seismic volume based on ranges and velocity values. The user then assigned individual colors and opacity values to the substances. By setting the opacities to 0, the user can make various substances transparent so that areas of interest can be isolated. Sun's visualization products provide powerful yet easy-to-use environments for scientists and engineers. Visualization techniques such as volume rendering can be effectively used to reveal new information about complex data.
Graphtals was originally developed for the interactive image show at the Museum of Science and Industry in Chicago as another way to visually and interactively explore mathematical concepts. It's now at the Computer Museum in Boston on permanent loan. Graphtals is an introduction to the idea of creating complex images from simple mathematical rules. It allows you to learn about them by controlling various aspects through the use of buttons and a joystick. Before we show you the game, however, let's cover a bit of Graphtal history. Graphtals are based on an area of mathematics. Aristide Lindenmayer, a biologist, adapted this branch of mathematics which uses a simple set of rules, called a grammar, to create complex forms. Lindenmayer's work became known as L-systems. L-systems produce results which resemble the patterns of plant growth and are used in biology to describe and predict how plants grow. Computer imagery can be used to imitate nature. Using the proper grammar, the growth of a simulated plant can be illustrated, from a single cell to a complex organism. Alvy Ray Smith adapted L-systems for use in creating shapes on the computer. Those shapes are known as graphtals. Now for the game. Written in an interactive language called RT1, Graphtals is designed for 3 levels of play: easy, intermediate, and hard. At any time during the game, the player can go to the Learn section to get additional information. This allows the player the choice to either jump in and play or learn more about the concepts behind the game. You can do it in any order and at any time. Let's try the first level of play. Level 1 first asks the player to select the number of repeats, that is, how many times the rules are applied in succession. Then it asks the color of the tree and what location to place it on the screen. The program then grows the tree, or graphtal, using the information the player has selected. Instead of going right to level 2, let's learn a little more about the concepts behind graphtals. computers normally need a lot of information to draw complicated objects, and natural objects, like trees, are quite complex. For instance, to draw a tree, you need to know the size and angle of each branch, where they're attached, and how many branches there are. In order to create natural shapes without using a lot of memory space, a programmer can use a set of rules called grammars to describe each branch of a tree. A grammar, however, needs some basic information or facts about the tree. A group of these facts is called a string. Repeating the grammar creates new trees. Although the trees are similar each time a grammar is repeated, it changes the string and alters the shape to create the new tree. To learn more about how the grammar changes the string, let's look at number 2. A graphtol tree is made up of branches. Each branch has one or more parts. Those parts are described using 1 or 2 facts, shown here in blue and yellow. The graphtol grammar is a set of substitution rules. Each time the grammar is repeated, each fact is replaced with 1 or more new facts. The changes can be starting a new branch, adding to the branch length, or ending a branch. If we use the blue and yellow parts we showed earlier and apply a grammar which has 2 substitution rules, the colors would be replaced as indicated by the diagram on the right. If the part is blue, replace it with a yellow. If the part is yellow, replace it with a yellow and an angled blue. If a new part falls directly on a previous one, then it is drawn at a different angle. Level 2 is played the same as Level 1, except now we can also select which grammar or set of rules to apply to our graphtol. Here we'll select our number of repeats, from 1 to 26, and use the joystick to pick the angle of the branches. There's a variety of colors to choose from. Let's select one. Now, place the graphtol on the screen. By experimenting with different combinations of selections, you can see their effect on the graphtol itself. While using the game, you'll also notice that sometimes the computer even adds leaves to a graphtol. We now know that in order to draw a graphtol, we need a string which contains some basic facts about the graphtol, such as the blue and yellow branch parts. And we need a set of rules, or grammar, to apply to the string. But how does the program see the string? The computer program needs symbols to name branch parts. Here we've defined our blue parts as the symbol 1, and the yellow parts as the symbol 0. These 1s and 0s are what goes into the string in the computer program. Brackets are the directions for tree growth. The left bracket tells the program to begin a new branch at an angle. The right bracket is the command to end a branch. 1s and 0s used between the brackets define a branch drawn at an angle. After the right bracket ends a branch, the computer returns to the previous branch to continue the facts from the string and draw the next branch. Earlier, we discussed how the grammar substitutes or replaces facts to change the description of each branch part. The program applies the grammar to the symbols 1 and 0 and the left and right brackets to change the description of the branch parts. For each symbol, the grammar has a replacement rule. If the symbol is a 1, replace it with a 0. If it's a 0, replace it with a 0 and a 1 enclosed in brackets, just like you see on the screen. The brackets are copied, but they're never changed. These replacements continue in the game until the number of repeats selected has been attained. That is, how many times the grammar is applied to the string. When you program a graphtol, it's the same thing. You have to define your initial string and how many times the grammar is applied to the string. Since we now know more about how a program uses strings and grammars to create graphtals, let's play level 3. Level 3 is similar to levels 1 and 2, except now you can select your own string. You can also reapply the same string to different combinations of selections to create new trees. We've selected the numbers shown below as our string. Let's now apply a grammar to that string. Once again, select the number of times to apply the grammar. And the angle of the branches. Next, the color. And finally, place the graphical and see what our tree looks like. What you can learn from this game is that graphtals use symbols as instructions for drawing. Branch color, length, angle, and thickness are defined independently from the string and grammar. Opening brackets help to make graphtals look lifelike. Nesting brackets within each other and using different angles or groups of angles helps to change the growth patterns. Although the graphical game applies leaves randomly to its trees, when you program a graphical, you can use the closing brackets to add leaves to the end of your branches. Remember, all of the elements of the graphical game can be applied to programming graphtals. It's just that the game is a lot easier and much more fun. We hope you'll visit the Computer Museum in Boston and try it for yourself.